right, is with respect to something, it's always up to us to choose what our reference point is. The most common reference point for electric potential energy is infinity. Okay, because infinitely far away, there are no fields, right? You are infinitely far away from any charges, any source of fields. Infinitely far away, there are no fields, so it seems to be a very good reference point because very far away, there's no work done, and no charges around. Okay, so using my definitions, I can actually obtain an expression for capital V for point charge. Okay, we already know that for electric field for point charge is KE. Right, I don't know if you guys remember, I'll just write it down in case of code. Right, E field is KE Q over R squared R hat. Right, so if you take this expression, which you saw last week, right, in both the lecture and the tutorial, and substitute this into this definition of voltage or definition of electric potential, equivalently speaking, then you will end up with this. Okay, and you can try it out for yourself in mathematical exercise. I think you would have covered it in lecture, but if not, try it out for yourself. If you have any trouble, yeah, I'll be more than happy to show you. Right? But it should be quite easy. Okay. So yes, question. So there are three, I understand there are three sets of documents, right? So this is the second document for electromagnetism. Yeah. Okay, so, right, yeah, the significance of the electric potential is work done per unit charge. So when you're talking about potential energy, which is voltage multiplied by charge, aka work done per unit charge multiplied by charge. Not surprisingly, the significance of potential energy is also the work done to move the charge from one place to another place. Okay, so if you consider the potential energy with infinity as a reference, that is equivalently, right, the meaning of it is the amount of work you need to do to take an electric charge from infinity and bring it all the way to the current point in question. Okay, that's the meaning of the potential energy. Okay, so far this top part has to do with, what does it have to do with? It has to do with obtaining the electric potential from the electric field. Okay, and you can see that you need to do an integral. Not only that, it's actually a three-dimensional integral. It's right, you've got to do a dot product between E and ds, and then do an integral from A to B. Okay, now, how do you recover E? If I give you V, right, the potential, how do you recover the electric field? The answer is this formula. Okay, you need to do something called a vector differentiation. This operation is also written mathematically like that. Okay, this upside down triangle is called the gradient. Okay, basically it takes a scalar, which is V in this case, right, and applies this operation to it. X hat del over del x, y hat del over del y, z hat del over del z. Okay, or k hat. Okay, right? It depends on what you call the unit vector. Okay, so you can go both ways, right? Given the electric potential, you can calculate what is the, so given the electric field, you can calculate what is the electric potential it sets up. Given the electric potential it sets up, you can calculate the electric field it sets up. Right? So they are quantities that they are closely related that you can derive from one another. Okay, any questions on this before we move on to capacitors? Okay, so you should already be familiar with this through the lectures, right? But feel free to interrupt and ask any questions. Okay, so the second part of the formula sheet I want to talk about is the capacitors. Okay, so how many of you guys have experience with resistors? You know, resistors in series, resistors in parallel. Who remembers calculating this before? Right, there are resistors in series. I heard 1 over R, that's very good. Okay, that's very good, right? Right, that's for what, you know, resistors in parallel, right? 1 over R equivalent equals 1 over R1 plus 1 over R2. Right, if you are adding two resistances in parallel. Right, how about resistors in series? If I have two resistors in series, R1 and R2, what's the total resistance?
R3.
Yeah, very good, excellent, R1 plus, there is no R3, but thank you for your contribution. Right, R1 plus R2 is the correct answer. Okay, now we are going to talk about combining capacitors, right? In the same way, capacitors can be combined in series and also in parallel. But the convention is the other way around. Okay, if you can remember for resistors, you will have no problem remembering for capacitor. But you need to remember it upside down, it's the other way around. What do I mean by that? If you have two capacitors in series, you are actually going to add them up this way. Okay? Which you might say, hey, that's the formula for resistances in parallel, and you're right. Okay, that's how it works. Right? If you have capacitors put in parallel, you're going to add them up this way. Okay, other interesting facts include the fact that the total charge separation in a capacitor is given by the capacitance multiplied by the potential difference. Okay, so the greater the potential difference, the greater is the charge separation in the capacitor. You can actually think of the capacitor like a battery, because you can actually discharge the capacitor and get current running in your circuit. Right, and what's storing the energy is this separation of charges. And what's the energy stored? Right, it is given by this formula, Q squared over 2C. If you know your charge separation and you know your capacitors, and by the way, capacitance is a fundamental property of capacitors, just like resistance is a fundamental property of resistors. Okay, if you know your fundamental, if you know your capacitance, you can use that to calculate the total energy stored. Okay, any questions before we get to our first question? Okay, if not, first question is on electric potential. Okay, you are given an electric field and you want to calculate the electric potential. Okay, so you have a uniform electric field of this magnitude. You are here a lot of buzzing, okay? So in the interest of your classmates who are trying to pay attention, right? Let's not discuss other topics. And if you have any questions, right, feel free to raise them so that we can address it as a class. Okay? So no question too small, right, for this class. Okay? So your uniform electric field is this amount and it's pointing in a downward direction, or more technically speaking, in the negative y direction. Okay, and you are given three coordinates A, B, and C. Right, this whole question is about calculating the electric potential difference of one point with respect to another point. Okay, so what is the potential difference of VAC and VCB? Okay, note that VAC is VC minus VA and VCB is VB minus VC, right? So you are trying to calculate the potential of C with respect to A and also B with respect to C. Okay, how do we go about it? We are going to apply the formula in the formula sheet, right? This is a problem that is, you can say it's a very straightforward application of the formula in the formula sheet. Not surprising because it's question number 1. Okay. What you want to do here is, but what's important is how to apply this formula, right? Sure, you might know this the formula to apply, but you might apply it wrong. Okay, so we already know that the definition of the electric potential is given as such, right? It's the vector integral of the electric field, right? Path integral of the electric field, right? But this path integral is from where to where, right? Is it from North Spine to South Spine, or from your home to NTU? Or, right, in this case, it's from A to C. Okay, and the reason is because we are calculating the potential at C with respect to point A. Okay, if it was not VAC, it was VCA, then you are going to reverse these two already, right? It's going to integral from C to A. Okay, so you've got to be very careful where's the start and where's the end, right? Integrating from A to C is not the same as integrating from C to A, right? You're actually going to get the same answer except for minus sign, but right, even the minus sign matters, right? As far as the accuracy of the results. No. Okay, so the rest of it is you want to have right, the electric field vector dot ds. Okay, so can someone tell me, so let me know if you have any questions about this. If not, I want someone to tell me how did I get from this working to this next part. Okay, right, you can take picture of this, but there's no one to explain to you what the working means when you're staring at it hours before the end of hours before your final exam, for example, right? So I'm here to explain it right now. Okay, so we'll go through this piece by piece. right? To make sure you understand. Okay, so can someone tell me how do we get from this step, right, this second step, to this step? Right, what change did I make? Right, not many change. I replaced E dot S with E ds cosine 180 degrees. Wow, how did that happen? How did I pull that out of the head? What is the reasoning behind it?
I forgot what it is. Something from
Sorry.
is it like something from
Something
change the form?
We are changing the form, right? The way it's written, we are expanding it.
So is it like polar notation or something?
Sorry.
Say it for me.
Like changing to polar notation.
Is it like changing to polar notation? I think, okay, when we say polar notation, I have a feeling what you're referring to is going from coordinates x, y to coordinates r theta, right? Where x is equal to r cosine theta and y is equal to r sine theta. So not quite, yeah, not quite. I mean, we might have a reason to do something like that, you know, but not right here, right? Not yet. Yeah. Yeah. But you're right in the sense that there is something related, or rather you are close in the sense that it's something related to angle. Yeah, it's something related to angle, right? That's why we have a cosine something over here. Right? But no, we are not changing our coordinate system or anything. Actually, we don't even define our coordinate system. We just go straight from this. Yes. Okay, so, okay, I like the answer, you know, I think you are at the answer, or at worst very, very close. Okay, I like the answer. Right, so what this gentleman said is, because we are traveling from A to C, and it's in the opposite direction of the electric field, okay, if I might paraphrase a bit. Okay, excellent, right, that's right. Okay, why is that so? Because this ds is a vector. Okay, this ds is a vector pointing from A to C. Okay, sure, it is a differential, it's a very, very small segment of the path, but nevertheless it's pointing in the direction of the path you're walking. Right, and this E field is just a good old E field which is pointing downwards, pointing in the negative y direction no matter what. So when you do a dot product, right, between E and ds, right, you want to recall the definition of a dot product firstly, which is magnitude of E multiplied by magnitude of ds cosine theta, right, where theta is integral in between there. Okay, in this case theta is 180 degrees. Why? Because from A to C, my path is going upwards, but the E field is going downwards. So you can see there is a 180 degrees difference between these two arrows. Right? Therefore, you have 180 degrees there. Okay, any questions about going from this step to this step?
The move of a field, right? The direction of the field.
Okay. So if not, then actually, you know, congratulations, the problem becomes very simple because cosine 180 degrees is just -1. If you didn't memorize this, your calculator will tell you it very easily. Right? So this guy will nicely cancel out this guy. So just an integral from A to C E ds, which is just E multiplied by the length AC. Okay, and that's all you need to do. You just take, right, reduces to such a simple calculation. E field multiplied by the distance, right? E field in volts per meter multiplied by the distance in meter to give you the answer in volts, 260 volts. Okay, any questions about how we figure out VAC is 260 volts? Okay, now we are going to do the same for VCB. Okay, VCB we are going to apply our definition again. We see CB meaning voltage of B with respect to voltage at C. That means we want to integrate from C to B, not from B to C, from C to B. Okay, we apply the same formula again. E is still pointing in the same old negative y direction, but this time it's making a 90-degree angle with ds. How do we see this, right? We are going from C to B, so ds is pointing in this direction. Okay, and can you see that we are making a 90-degree angle to the E field? So it's cosine 90 degrees, right? Cosine 90 degrees happens to be 0. Okay, if you don't remember, once again, your calculator will be more than happy to tell you in a few seconds.
Origins always here, right?
Okay, and what we find is that the potential at B with respect to C is equal to 0. Right, so if you recall, so if these were wires, right, and you recall the stuff you learned about electricity in the past, right, if AC was a wire, then there could be current flowing along VAC, right, but if CB is a wire, there will be no current flowing along CB because there's no potential difference, there's no force per unit charge to move any charges. Okay, and if you want to calculate VAB, you can just add VAC plus VCB to get 260 volts. Okay, and now I want to ask you guys why. How do I know that VAB is equals to VAC plus VCB? Pythagoras' theorem was a suggestion actually. I sort of like the suggestion, but it's not quite, doesn't quite hit the mark because this actually works even if AC and CB are not at an angle, not at a right angle. Right? In fact, if you have any 2 points, or sorry, any 3 points, right? Let's say X, Y, Z, okay? Like X, Y, sorry, let me get this straight. VYZ plus VZY will give you VZX. Right? So it works for any combination of or maybe I'll just call it ABC, so to be simple. Right? This formula for ABC, it works regardless of my angle. Okay, but Pythagoras' theorem works only for right angle, right? So how do we know that VAB equals to VAC plus VCB? Okay, so some students suggest vectors, right? They say, oh, it's basically vector addition. Okay, oh, you know, if you have a vector, right, AB and a vector BC, if you want to get vector AC, you can add these two up. That would be reasonable intuition, but it's actually also not completely correct because my voltage is not a vector. My voltage has no direction. You know, I say VAB is voltage at point A with respect to voltage at point B, is a scalar quantity. Right? VAB is 260 volts. It's not 260 volts in the northwest direction. You know, it's not 260 volts in the pointing into the page. Right? So the answer actually is simpler than you expect. It's just the definition. Okay, so VAC is defined as VC minus VA. Right? So VAB is VB minus VA. Right? And then VAC is VC minus VA. Right? VCB is VB minus VC. What happens when I take VC minus VA and subtract that from VB minus, make this legible. Okay, subtract that from VB minus VC. Right, you'll notice that this VC and this VC cancels out, and you end up with VB minus VA. Let me see, sorry, these are plus. Okay, so these two cancel out, and you end up with VB minus VA. Right, so left hand side equals right hand side. Okay, so the reason this formula is correct is just because of the definition. Okay, and this is a very smart way of figuring out that VAB is 260 volts. Okay, but the next part of the question asks you to directly calculate VAB. Okay, to check that the formula, the result for VAB really is correct, even if you do it the vector integral way. Okay, so we can do it the vector integral way, no problem, and certainly we expect to get the same results. Oh, sorry, there's something else. Oh, you're supposed to comment on the electric potentials at point A, B, and C. Yeah, fine, right? You notice that VB is equal to VC, so point B and C, they are lying on the equipotential plane. Okay, and which is normal to the E field. It's just like gravity, right? Like equipotential plane for gravity is also normal to the gravitational field. Okay, and right, we are all at the same potential energy. Why? Because we are along a plane which is perpendicular to the gravitational field, which is pointing downwards. Right? So it's the same for electric potential. Okay, we know that VC and VB are greater than VA because there's a higher potential. It makes makes sense because electric field always points from higher to lower potential. Okay, just like the gravitational field also always points from higher to lower potential. Okay, and part B basically requires us to calculate this VAB using the integral, right? Directly using the integral from A to B. So this is a good chance to test ourselves and make sure we really understand this vector integral. Okay, so we are integrating from A to B because it's VAB, right? Minus integral A to B E dot ds. So far so good. Okay, right? And now the question is, how did I end up with cosine pi minus theta? Okay, right? Once again, it's actually not very difficult to figure out. This angle is simply the angle that E makes with ds. Okay, E is pointing downwards. ds is pointing in which direction? Okay, I heard upwards, which is, if I read you correctly, you mean upwards at an angle, right? Right? Upwards at an angle, right? Along, got to be along the path. I didn't draw this straight. Okay, so right upwards along this line, right? Okay, so this is ds, right? This is E. And what's the angle in between them? Can you see that it is 180 degrees minus theta? Okay, that's exactly what pi minus theta means. That 180 degrees is pi in radians. Okay, and you punch in your calculator, or you just remember your geometry identities. Cosine pi minus theta is simply minus cosine theta. Right, that allows you to bring out the cosine theta here and neutralize this minus sign in front. Right, so you get once again E cosine theta multiplied by this integral over the path, which is E cosine theta multiplied by AB. Okay, so the length of AB happens to be greater than the length of AC by a factor of cosine theta. Hold on. Yeah, the length of AB happens to be greater by than the length of AC by a factor of 1 minus cosine theta. So AB is simply AC divided by cosine theta. Right? If you don't want to reason it out this way, you can also apply Pythagoras' theorem, right? AB squared is AC squared plus CB squared, okay? And you end up with the same result, which is that the potential of B with respect to A is simply E multiplied by AC 260 volts once again. Okay, so it's a sanity check. And that makes sense, right? Physics, you can calculate it many different ways, but you always end up with the same result. Just like you can go from the north spine to the south spine in many different ways, right? But the south spine will always be the same, regardless of which path you use to initiate. Okay. In conclusion, we are obtaining the same result in part A because the electrostatic field is a conservative field, right? Just like the gravitational field. Okay, meaning that the work done doesn't depend on the path. Okay, any questions? Okay, so let's move on to our next question. Can I have a check, is this your next question? 3 charges at the vertices of... Okay, so you have 3 charges at the vertices of an isosceles triangle. We saw this before. Okay, but back then, what were we doing? We were very obsessed with calculating the electric field. Okay, today we'll be very obsessed with calculating the electric potential. And we will see that there is a relationship between electric potential and electric field as per the formulas you already saw in the formulation. Okay, so let's go about doing this. Okay, the electric potential at the midpoint along the base, right, is this point, and we simply obtain that by summing up the contributions of all of the different charges. It's just like electric field, If I'm going to ask you to calculate the electric field at this point, midpoint of the base, right, this red circle over here, you're going to add up the electric field contributions due to the 3 different charges. That's the exact thing we do when we're dealing with electric potential. We just add up their contributions. Okay, and this is even easier than electric field because electric potential is scalar. You don't need to add up 3 vectors, you just add up 3 scalars. Okay, so, right, this R1 is 0.0387. Why? Because that's the distance we have between the point in question and the charge 2Q. And then there's 0.01, which is basically the 1 centimeter distance it has, that there is between the midpoint and the -2 charge. Okay, so really pretty straightforward, direct application of the formulas. right? Of course, having said that, in an exam, it's very important to know which formula to apply, right? But maybe once you do, you know, a lot of problems will turn out to be very simple. Okay, so in this case, you recognize that it's electric potential problem, and you apply and you are able to know, right, what Q belongs to which term, you know, and what are the distances to use for each Q. Yeah, you know, it's going to be a very easy question. Okay, right, potential can be negative, okay, minus 13.33 megavolts. Okay, any questions on this electric potential? It's just like summing electric field, right? But you're summing a scalar except a vector, which means it's easier. Okay, now the next part of the question asks me for the work done. Can someone tell me, given that I've already calculated electric potential, how do I calculate the work done? Very simple formula relating work done and electric potential.
Times.
Yes. Yeah, that's the first part of the right answer. I give you 50 marks directly out of 100. Okay, you're multiplying something with something.
E times
Okay, V times,
C. Oh, no, what?
not C. Okay, exactly, very good. Q.
I
Okay, right? So the work done, aka, and another word for work done is also electric potential energy. Right? I mean potential energy, right? I mean the reason I gain potential energy moving from the first floor up to this floor is because I climbed the stairs, right? I did work on myself, you know, right, to bring myself up here. That's why potential energy. Right, I don't get potential energy out of nothing, you know. Okay, so right, the work done came from the chemical potential energy from my dinner, I guess. Right, so right, work done and potential energy are very closely related. Okay, potential energy is stored power, and work done is the work you do to create that stored power. Sorry, stored energy. Right, so here simply you just multiply by the charge in question and you get your answer. Okay, easy peasy. Now let's move on to part B. Okay, determine the total potential energy of this system of three charges, right? So they're asking us what is the total potential energy possessed by these three charges. So potential energy is stored energy. So can someone tell me, looking at these three charges, why would I say this is a form of stored energy?
Because it's not moving.
Okay, it's not moving. That's part of the answer. But how do I see how do I see this converted to, let's say, kinetic energy? Like for instance, I'm standing on this floor. How do I see my gravitational potential converted to kinetic energy if I jump down, right? I'll hit the ground at very high speed, which is not good. But let's say if it's not me, if let's say I am, I don't know, let's say some mechanical process, right, where you are pounding something, then it's very good to let it drop from a height. Right, I'm converting potential energy as a stored energy to kinetic energy. So how do I see this as a form of storage? Well, I'm storing potential energy that can be potentially converted to kinetic energy, right? That's where the word potential comes from, potential energy.
Charge. What?
Okay, remember these are plus charge and these are two minus charges. What happens when you let them go? What happens when they're not held in place? Are they going to stay where they are? No, right? It's just like if this floor wasn't underneath me, I'm not going to stay where I am. I'm going to fall down and have my energy, potential energy converted to kinetic energy, right? Which in my case is not good, obviously, right? In this case, you have a system of charges and you're supposed to assume, yeah, these charges, they are fixed in place. How you know we don't know they are fixed in place, right? But the reason they have potential energy is because if you let them go, right, whatever is fixing them in place is no longer there, right? Do you think these two negative charges will be so happy to stay near each other? No, they won't. They'll fly apart, you know, and this positive charge, right, it might try to approach the negative charges, but the negative charges will probably fly apart even faster. I mean, depending, you know. Actually, let me see. Sorry, the potential energy is negative, so I think this system will attract. Yeah, this system will collapse, right? This positive charge and this negative charges will fly towards each other and explode. Oh, well, explode, maybe implode, you know, I don't know what's a good word to use. They'll fly together, right? And when charges move, you know, I mean, it can potentially be a source of work done. When charges move, when they accelerate, they radiate, they lose energy. This energy can be used for doing things. For example, okay, so this is a system that is storing energy, right, in the form of potential energy. And this question is asking us, what's the total potential energy? Okay, as we already mentioned, total potential energy is simply equivalent to work done, right? And in this case, it's equals to the work done in assembling this system. So what we need to imagine is if these three charges started off in infinity, where no fields exist, and I take them one by one, okay, and arrange them in this formation. What is the total work I need to do to assemble this system of three charges? Okay, so that will give me the total potential energy of this system, right? So first of all, okay, so here is the full solution, but just focus on this first term for now. If I were to ask myself, what is the potential energy, or actually, you know, let's not look at any of the terms. Okay, what is the potential energy needed to bring this 2q charge? Okay, imagine I don't have any charges. If I take the 2q charge from infinity and bring it all the way to this point on my screen, how much work do I need to do? There is no field, right? There is no field anywhere because there are no charges present right now. Now I reach out to infinity and I take the 2q charge and bring it onto this screen, right, where there's currently no field. How much work do I need to do? Zero, very good, because it's moving field free. Okay, now this is done already. Okay, now I'm going to bring the minus q charge from infinity to the screen. Is my work done still zero? Now we have the 2q charge present here. It's producing an electric field. Very good. It's no. Okay, and the reason is because the minus q charge, when I bring it from infinity onto my screen, is going to start to move in the electric field produced by the 2q. And whenever a charge moves in the electric field, you need to exert work. Right? You need to do work. Either it's negative or positive, but you need to do work. Negative just means you are keeping it from accelerating, okay? Positive means you are pushing it, right, in the direction that you're moving. So this negative and positive, don't let that confuse you, okay? It just refers to the direction that you exert the force with respect to the direction that the particle is moving in. Okay, so work done is very normal to be negative or positive. Okay, so that's where this first term comes from. Okay, in case you're wondering, this is the work done to take the negative q charge from infinity and bring it onto this screen in the presence of the 2q charge. Okay, and the way you can see this is that Ke2q over 0.04, this is the electric potential produced by 2q. Okay, and this minus q is simply this formula over here, right, where this q is minus q, and I'm multiplying it by capital V, right, where capital V is this, right, this is the capital V due to the 2q charge. Okay, so once again, this is an application of work done equals q times V. Okay, and also an application of the capital V of a point charge is given by Keq over 0.0, or over R, right, Keq over R. Okay, so now that we have two charges out of the three charges we want to assemble in the system, I will now start to bring the third charge, which is the minus q charge from infinity, into the presence of these two charges. But these two charges, they already set up a static electric field, so my third charge is moving in this electric field. And because it's moving, yes, you know, I need to do work to move it to the right position. And the amount of work I do is given by these two terms. One term because of the existing 2q charge, and the other term because of the existing minus q charge. Okay, because each of them set up their own electric fields, right? Each of these electric fields, they are associated with electric potential, and I need to multiply the new minus q charge with each of these electric potentials to get the work done. Okay, so that's how you get the total energy of the system of three charges. So whether it's 3 or 5 or 300 charges, this is the way that you're going to do it. Of course, 300 charges don't be incredibly complicated, right? You need a computer, and at some point even the computer cannot handle it, right? But that's how we calculate the total energy of these three charges. Any questions? Okay, yeah, this represents the energy required to assemble the system of three charges. Okay, any questions on question 2 before I move on to the next one? Okay, and can I ask, is this the next question? No, okay. Is this the next question?
No.
No, okay.
Two charge
Here,
Spherical.
okay, two charged spherical conductors are connected by a long conducting wire. Okay, and I want you to call your mind back to last week's tutorial, where we also had two charged spheres, or rather one charged sphere and one uncharged sphere, and they kept touching each other, remember? Actually, it was two charged spheres, sorry, that was question 1, right? They keep touching and being separated from each other, right? And each time they touch, remember we take the total charge and divide it by 2, right? Because charges are free to flow. Okay, now I want to remind you that the reason we can do that is because the spheres are equivalent, they are of the same radius. That's why it's so simple when they touch, charges are free to flow. Since the two spheres are identical, the charges will not prefer one over the other, so they'll flow to fields equally, you just divide by 2. Now here you cannot assume it's the case. Here once again I have two spheres that are touching, okay? I mean, they are touching via a very, very long wire, okay? But that's still that's essentially they are connected, right? And charges are free to flow. Okay, we cannot simply take total charge divided by 2 this time because these two spheres, they are not equivalent. So I want to ask you, okay, what's your ratio? Yes, there's a ratio involved, very good. Okay,
4 and 6.
Sorry.
4 and 6.
4 and 6. We'll see, okay, we'll see. Okay, we'll see. I think that you might be close, yeah. Okay, but we'll see. Okay, yeah, 4 and 6 is probably quite close. Okay, so okay, the reason I say close is because you know, right, is it 4 here and 6 here, or is it 6 here and 4 here, right? So later we will see. Okay, but okay, never mind. Okay, never mind how he got that. Yes, right. I would like someone to tell me what quantity would you take into consideration, you know, to figure out how to distribute the charges, right? Or right, you chose radius. Why do you choose radius? Why did you not choose r squared? I mean, the surface of the sphere is proportional to r squared, 4 pi r squared. Right? Why not r squared? Why not r cubed? Why not r to the power of 10? You know why do you choose r? Right? Would someone like to help me out with some intuition? What needs to be equal when 2 points are connected by a wire? When 2 points are connected by a conducting wire, what needs to be equal? You think about your electric circuit. Charge does not need to be equal. Okay, charge does not need to be equal. 2 points are connected. What needs to be equal?
Force.
Sorry? Otherwise, there's a short circuit. Okay, if it's not equal, there's a short circuit. What needs to be equal? Not force. Voltage, very good. Okay? So, when you have these two spheres being connected by a wire, the voltage on their surfaces must be the same, aka the electric potential on the surfaces must be the same. Do we have a formula for the electric potential on the surface of the sphere? Yes, we do actually. Okay, if you have forgotten that, it's covered in the lecture, don't worry. But it's actually the same formula as for point charge, so it's very easy to remember. Okay, so sorry, it was supposed to be a quiz. I guess I preempted myself. Okay, yeah, what does it mean that the two spheres are connected by a wire? Do they contain the same amount of charge? No. They are the same electric potential? Yes. Okay, and C and D is not correct. Okay, B is the correct answer. Okay, very good. Okay, so if we let the radii of the two spheres be R1 and R2, and the corresponding charges that are built up to be Q1 and Q2, we can actually, okay, sorry, and yeah, there's some assumptions over here. They need to be separated far apart, and now, because if they are too close, the charge distribution will not be uniform, they'll start to distort each other's charge distribution. So we want to make it a very ideal problem that we can solve easily, right, in the classroom. Okay, but those assumptions aside, right, basically, what we can do is, okay, I don't think I want to go through it. Actually, this part is the derivation for the potential on the sphere. And the solutions, they provide this derivation, but they're also in your lecture notes. So I would say, in the exam, you just start on this line, right? And this line is something you recognize also from the formula sheet. It's the same expression as the point charge. Okay, so I'll just let you guys take a picture of this. If you want to ask more questions for derivation, more than happy to talk to you about it, but it's pretty straightforward and covered in the lecture. Bottom line is potential on the sphere is KQ over R. Okay, and you want to equate the potentials. Okay, so you see here's the ratio of R1, here's where the ratio R1 and R2 come in. Okay, so you want to equate their potentials. KQ1 over R1 equals KQ2 over R2. And as a result, Q1 over R1, and you just rearrange that, we cancel K on both sides, and you just rearrange the math. Q1 over R1 is equals to, sorry, Q1 over Q2 is equals to R1 over R2. Right? In other words, the bigger the radius, the more charge you can accommodate, which in some ways makes sense, right? Because the charge can space themselves out more. Okay, but I guess the counterintuitive thing is it's not proportional to R squared. Right? Intuitively, you might expect proportional to R squared because that's the surface area of 4 pi R squared. It's not, you know, and the reason it's not is because potential is proportional to 1 over R, not 1 over R. Okay, so right, we are not at the end of the problem. This is only the first piece of the puzzle. Okay, we also have the fact that the total charge is 20 microcoulomb. Now we have two equations in two unknowns. We can easily solve this problem, right? Easily solve for Q1 and Q2. Okay, you will get Q1 is 8 microcoulomb, Q2 is 12 microcoulomb. Okay, any questions on part A? Okay, if not, then let's look at part B. The electric field near the surface of each sphere. Okay, so this is actually not a problem that belongs to this week's strictly speaking, because it's asking us for the electric field. Okay, we already learned about the electric field last week, right? And as we recall, the formula for electric field, whether it's a point charge or whether it's a sphere, is KEQ1 over R squared. Okay, so just put in the, just plug in the quantities into the formula, right? They're all in the question, and you're going to get an answer. And by the way, this is an example, oh sorry, I was going to say this is an example of where you can solve part B without part A, but actually no. You need part A to solve part B in this case because you need the values of Q1 and Q2. Okay, so you have to plug it into the expression for electric field and solve for the electric field, which is given by this. Okay, yeah, the direction is not indicated here. I guess they're only asking for the magnitude. Okay, but it's pointing radially outwards. Okay, radially outwards. Yeah, I guess the solution is not complete here, right? They say electric field, they didn't say the magnitude of the electric field. But I guess there's a hint that you only care about the magnitude because the answers provided to you only have the magnitude. Okay, but if you're wondering what direction is pointing in, the answer is radially outward. Okay, like a porcupine or like a hedgehog pointing outwards. Okay, in an R-head direction. Okay. And question C is even more basic, you know, it's asking for the potential at the surface of the sphere, which is what you had to equate in part A in the first place to calculate what's Q1 and Q2. Okay, so yeah, just plug that in, and of course you should get the same answer, right, for both 1.8 megavolt. Okay, so what happens when you have two charged spheres and connect them with a wire is that the charges will flow in between these two conductors and redistribute themselves until the amount of charge in the two spheres is the same as the ratio of their radius. Okay. Okay, any questions? Okay, and do we have this question also? We do, right? Okay, so let's determine the equivalent capacitors, okay, for this. Okay, let me go a little bit faster because I think it's quite straightforward, right? I mean, you guys sound like you're pro at resistors, but slow me down if I go too fast, okay? Don't worry about interrupting any kind of comments. Okay, so here you want to calculate the equivalent capacitors for, let's say, the middle portion, right? So it's C over 2, right? And then you can end up with a series of parallel, right? You deal with the ones in series first. Okay, then you end up with a parallel configuration, then this is for equivalent to, okay, you are adding up 3 C's, okay, or 1 over C plus 1 over C plus 1 over C, and inverting it. Okay, and yeah, the parallel, you just sum up the capacitors. Okay, so it's the same treatment as resistors, but the opposite convention. Yeah, so takes a little bit of getting used to, but that's straightforward. Okay, part B. Okay, part B is this, right? You know the trick with these capacitances questions is what order to simplify them in, right? So you always want to deal with all the series first, right? And then you deal with the parallel and so on. Oh, you're gonna, yeah, and then go step by step, basically simplify step by step. In this case, you want to deal with the series here, C1 and C2, right? To get C equivalent 1. Then you want to convert this parallel one to C equivalent 3, and then finally add these two components up. Right? Or rather not add them up, I mean, invert the sum of their inverses. Right? So C equivalent 1 is given by, okay, C1 plus C2, right? Let me know if you see anything that you disagree with, right? Or you're not sure about. Okay, C equivalent 2 is just C2 plus C2, right? Simple, right? It's in parallel. C equivalent 3 is 2C equivalent 1 plus C3, right? It's just dealing with this guy. Okay, to get C equivalent 3. Right, and finally the result is obtained by combining these two capacitors in parallel. Okay, 6.04 microfarad. Okay, any questions? Okay, if there are no questions, then okay, then here's the third question, right? You are given this circuit, and this time, you know, you actually have a battery here, right? 50 volts, and yeah, please excuse the pixelation, right? This 40 microfarad, 60 microfarad, 25 microfarad, and I've added this as my own working, right? The charge separation, right? Of course, plus Q1 has to have minus Q1, right? Capacitor is neutral, the entire circuit is neutral, right? So, okay. One trick to solving this question, or one key step to solving this question is realizing that because the circuit is neutral and every portion of wire is neutral, if you were to combine these two capacitors, right, this guy has to have plus Q charge, this guy has to have minus Q charge, they have to have the same. It's not just the charge separation has to be the same on either plate. I mean same in magnitude or opposite in sign. Even, right, from one capacitor to another, it's actually the same amount of charge separation. Right, because it's a neutral wire, right? If you pull minus Q of charge to here, you have an excess of plus Q of charge left over here. Okay, so you want to use this to solve your problem basically, okay? The C equivalent is just a sum, right? I can just sum the capacitances of these two up, right? And then the potential difference, the total potential drop delta V, which is 50 volts, okay, is given by the drop over capacitor 1, which is this guy over here, plus the drop over capacitor 2, which is this guy over here. So please remember the formula from formula sheet that voltage is equal to Q over C. We have a question? Yes, we have a question.
No, I'm
Oh, sorry, I just checking. Okay, fine, yeah. Okay, so remember that voltage is Q over C, right? So add, you want to add up the voltages, right? And it has to be equals to 50 volts. Okay, so that basically tells you that the charge is equal to 1 millicoulomb, right? Right, after doing the math, you get that the charge is 1 millicoulomb. Okay, so then you want to find the potential drop over V1 and the potential drop over V2, because the question asks you for, you know, all the details of this circuit, right? It's going to ask you what's Q1, what's Q2, and even the energy that's stored by these capacitors. Okay, so first things first, you actually need what the potential drop is. So to calculate the potential drop over V1, you want to take Q divided by the capacitance of 1, right? Because you have already calculated what Q is, right? Doing that, this tells you that the drop over this first guy is 40 volts. And then doing the same for the bottom capacitor over here, or the side capacitor over here, right? You find that there's a 10 voltage drop, right? So 40 volt plus 10 volt, yeah, that gives you 50 volt total, right? That's the standard check.
KVL, KCL.
Right, and then you apply a formula, right? Q1 is equals to CV, right? Q is equal to 3, and you get 400 microcoulomb for Q1 and 600 microcoulomb.
C.
Okay, so that's how the charge is divided in between the both of them, right? 1 millicoulomb of charge in total, but this guy has 400 microcoulomb, this guy has 600 microcoulomb. Okay, and you have to add up to be equal to 1 millicoulomb, which is the same as the charge difference across this element 1. Okay, any questions? Okay, I'll show you the full answer. Okay, the last bit of the answer is very simple. You're just calculating the energy stored in the capacitor. Right, energy stored is given by Q squared over 2C. Right, so you know what Q is, you know what C is, you can do that for every single capacitor in this question. Right, of which there are just 3. Okay, and you get the answers 20 millijoule, 2 millijoule, 3 millijoule. Okay, any questions? Okay, then next question would be, okay, we are on to this question now, right? Right, this right hand rule and left hand rule, right? Okay, so basically, this part of the tutorial has to do with the Lorentz force equation, okay, the force exerted by electric fields, right? And you actually already know part of this equation. The force exerted by electric field is given by F equals QE. What this lecture introduces is that force can be exerted due to magnetic fields as well, but magnetic fields exert force on moving charges, aka currents. Okay, so if V is the speed of the charge, then the force exerted is F equals QV cross B. Okay, and the cross product is similar to the dot product, but now it has a direction. Okay, dot product means the scalar result has no direction. Cross product is the direction. Okay, the magnitude is AB sine theta, just like for dot product is AB cosine theta, right? Here is AB sine theta. Okay, and the way you want to calculate the direction of the cross product is by using your so-called right-hand rule. Again, when we say right-hand rule, do note there are many right-hand rules. Okay, so in this particular case, this is the one for cross product. Right, you have to hold up your hand such that your thumb, index finger, and middle finger are at right angles to each other. Oh, actually, sorry. Your thumb is at right angle to both your index and your middle finger. Index and middle finger do not have to be at right angles, they just need to be in the same plane. Then A cross B, represented by the index finger and the middle finger, gives you the direction pointing in, right, that your thumb is pointing in. Okay, so every time you do a cross product between two vectors, your result is always perpendicular to both vectors. Okay, we can write the equivalent formula for current as well, IL cross B. Okay, where L is basically the length of the current bearing element in question, right? And L is the direction of the current flow. Okay, now here there is another right hand rule. This right hand rule tells you how to calculate the magnetic field generated from the current. You want to point your thumb in the direction of the current, and the direction that your fingers are curling in gives you the magnetic field. Okay, and this is the formula for calculating the B field from a finite rod of current. So you need to use something called the Biot-Savart law, right? Which, okay, we could cover in lecture. Okay, don't worry if it's a strange name. It's covered in lecture, right? And the lecture shows you the derivation. Okay, so that's how we get this formula. Okay, but this is a very useful formula. I think later on we'll have a question where we get to apply this formula directly. Okay, so it's a useful formula to remember or to know. Okay, and then finally, right, we're going to deal with a charge. Right, our very first question is going to deal with a charge in a magnetic field, right? Moving charge in a magnetic field. What happens is this charge going to execute a helical motion. Helical motion means it's going in a circular direction, but as it executes circles, it's moving forward as well.
Customer or support.
Okay, so this tells us that you inject a charge into a magnetic field such that it has a component of velocity along the magnetic field and perpendicular to the magnetic field. The component perpendicular to the magnetic field is going to cause it to move in circles, while the component parallel to the magnetic field is going to bring it forward. Okay, so that's
It's a very small plug.
Right, the period of this is given by this formula, the radius is given by this formula. How did we arrive at this formula? That's in the lecture. Okay, this is the final result of the lecture. Okay, so here we have a uniform magnetic field directed along the positive x-axis, right? And a positron, which is a positively, which is similar to an electron, but it has a positive charge instead, right? Moving at a certain speed at an 85-degree angle. Okay, so can someone tell me, given these two formulas, I know my period and I know my radius, how do I calculate the pitch P, which is the linear distance traveled by the charge in one cycle? So this charge is like the car going up the multi-story car park, right? When your car goes up the multi-story car park, it's also moving in roughly helical motion. Okay, what is pitch P? How do we calculate it? Right, in the car park, it will just be the distance from one level to another level. Okay, how about here?
One wavelength.
Oh, actually, I like that, you know, that has the gist of it, okay, but we're not dealing with waves here, so the word wavelength is not the right word, okay, but that implies period and periodicity, so that's the right idea. Anyone wants to take another guess? Okay, yes? Plane. Yeah, sure. If we think of like the different car park levels as planes, the distance between the two planes, okay, is about 1, right? But that's the question, right? How to calculate the distance between these two planes or these two levels? Okay, so the answer lies in this period. Because what is period? Period is the time it takes for the particle to return to its original position, right? But at a different level. You know, your car goes out, or your motorcycle goes out the car park, right? The period, right, is the time it takes for your vehicle to go full circle. But we are not being asked for period, we are being asked for the pitch, right? But that's the relationship between distance and time, right? If I know the time it takes to make one circle, then the distance I travel is just my speed times the time, right? But we must be careful on the speed. One is the speed in the direction of x, okay? So you actually want Vx, okay? You don't just want V, right? So you want to take V cosine 85 degrees, which gives you V in the x direction, multiplied by the period, okay? And that gives you your pitch, right? And the radius of the trajectory is just copy and paste from the formula sheet. Yeah, you know, we have the formula for the radius, you derived it in lecture, we just apply it to this problem. We know what Vy is V sine 85 degrees, right? Just like Vx is V cosine 85 degrees, right? We know what the mass is, we know what Q is, we know V is, everything substituting, you get the radius. Okay, any questions? Okay, is this one of your questions, velocity filter?
Yes.
Okay, great. Okay, this velocity filter is really cool. Okay, basically you have two fields, an electric field and a magnetic field. Right, magnetic field is pointing into the pitch. Electric field is pointing downwards. Okay, and we are being asked to find the magnetic field such that 750 eV electron entering the filter will be reflected. Okay, so I hope you guys remember what EV means, right? 750 EV, right? It's just a unit of energy. Okay, so 750 EV is equal to 750 times 1.6 times 10 to the power of minus 19 coulomb voltage. Okay, so this part comes from E, right? E is the elementary charge, is a fundamental constant. You find it at the back of the exam, okay, in the formula sheet or the list of constants. Okay, and remember, charge coulomb times voltage, that is the definition of joules. Okay, so EV is just another way of writing energy, okay, right? So it's just a very small quantity of energy, right? 1.6 times 10 to the power minus 19 joules, that's what EV. Okay, so we are supposed to find the magnitude of E field such as 750 EV electron will not be deflected. So I want to ask you, okay, what are the forces exerted on the electron due to the E field and the B field? Okay, the electron is negatively charged, right? What direction, what force is the B field and the E field exerting on my electron? If the B field is pointing into the pitch and the electric field is pointing downward, is it in, out, up, down, down, up, or out and in? Who thinks the answer is A, in and out? E field is pushing
in
the
and out.
electron in.
In and out.
In and out.
And
You like in and out. Okay. E field is pushing the electron in. B field pushing the electron out. What about option B? E field is pushing the electron up. B field pushing the electron down.
Oh, down. This.
Okay, updated answer.
Wait. C.
Who thinks the answer is C?
C.
E field pushing the electron down. B field pushing the electron up.
Is it?
Who thinks the answer is D? E field pushing the electron out. B field pushing the electron in. Okay? I also need to figure it out, but there's a quick way of figuring it out. It's faster to figure it out for the E field than for the magnetic field. So let's do the E field first, because you can see the E field is in, up, down, and out. The moment I figure out the answer for the E field, I know what the correct answer is, even without looking at the E field answer. Right? Unless the answer is wrong, right? Which it can't be. Okay? So if the E field is pointing down, right? What's the formula for my force? I hope everyone remembers F equals QE. Okay, so if the E field we know is pointing downwards, but this Q, what sign is it? Is it positive or negative?
Negative.
It's negative, right? That means overall, exactly, you flip upwards. Okay, so the answer is B. Okay, okay, tricky question. Okay, tricky question. Okay, right? E field is pointing downwards, but the charge is negative. So F equals QE ends up being a vector pointing in the opposite direction upwards. Okay, and let's very quickly do the exercise for the B field together. Okay, the force for the B field is Q, B cross B. Okay, so please join me, right, in putting up your right hand like that. Okay, the thumb pointing out and the index finger and the middle finger also pointing out. Okay, and remember that index finger cross middle finger gives you the thumb. Okay, right hand. Okay, right hand. Okay, unless you are existing in a completely different unless you use a completely different coordinate system, which we showed you, because we use the right-handed coordinate system. Okay, so right, we want to do V cross V. Let V be my index finger, and I'm pointing forward, right? Okay, and let B be my middle finger, right? Notice that I can orient my middle finger to be pointing anyway, right? As long as my index finger points forward, but I'm oriented to point it into the pitch because the magnetic field is pointing into the pitch, right? Note the direction in which my thumb is pointing upwards, right? Okay, so why is the answer downwards? Because of the negative sign of Q. Okay, it flips the vector downwards. So indeed, the B field exerts a downward force. Okay, so V cross B is upwards, right? Remember my thumb was pointing upwards. Okay, but because Q is negative, this overall expression becomes downwards. Right, so the B field is downwards, so B is correct. Okay, for both B field.
Oh, this is force, this is B field, this is FBI, I remember it. FBI, open up, that's I remember it.
Okay. Okay, so what we want to do is want to equate the forces due to these two fields. Okay, the force must be equal in order for the particle to not be deflected. Okay, so I'm going to equate the force due to the E field, which is, right, the magnitude is given by EE. And the force due to the B field is EBB, okay, QBB, right, the magnitude. We only care about the magnitude now because just now we already established that they are pointing in opposite directions. Okay, so if I equate both of them together, right, okay, and I can calculate my, don't be intimidated by this, it's just a very quick calculation for the speed of the electron, okay, given the kinetic energy. So knowing the speed, I will find out that electric field must be equal to V times B in order for the electric field force to exactly cancel out the magnetic field force. Okay, and it must be 2.43 times 10 to the power 5 volts per meter. Okay, any questions? Okay, can someone tell me what happens if I send in a particle at a faster speed than this? Right, if I send it with a higher kinetic energy, will it deflect upwards or will it deflect downwards? Okay, if I send a particle with a higher, right? If I send a particle at exactly 750 eV, it doesn't get deflected, right? According to the E field I calculated just now. If I send it much faster at a much faster speed, will it deflect upwards or will it deflect downwards?
I don't know. I don't know.
Who thinks the answer is up? Okay, faster particle. Okay, this is a velocity filter, it's only picking up one energy, right? So what happens to the other kinetic energies? The faster particles and the slower particles will all be deflected. So they'll all go to the side. The only particle that makes it through in a straight line is the particle that you design this velocity filter for. That's why it's called velocity filter. Right, so now the question is, if my speed is faster than what I designed it for, will the particle be deflected upwards or downwards? Who thinks the answer is upwards? Who thinks the answer is downwards? Okay, the answer is downwards. Okay, and this can be a bit tricky to figure out. I didn't give you guys much time. Okay, so congrats to everyone who put up your hands, okay, for giving this problem a shot, basically. Okay, the reason is because the force exerted by the B field is pointing downwards. When your speed increases, right, so basically the force due to the B field is proportional to the speed. This is the force due to the B field, this is the force due to your electric field. The force due to your electric field is independent of speed, it will always be the same. When your speed increases, you are just increasing the force exerted by your B field, right, which is in the downward direction, so it will be even more downward and your particle will be deflected downward if it's too fast. If it's too slow, it will be deflected upwards, because the B field force is not enough to counterbalance the E field force. Okay, so that's how the velocity filter works. Okay, is this one of your questions? I might need to get you guys to take pictures of some of these questions. Yeah. Okay, but is this one of your questions? Okay, very good. Consider a wire carrying this current in the positive x-axis, right, and lying in a non-uniform magnetic field. Okay, given like this. Find the magnetic force on a section of wire between x equals 0 and x equals 2 meters. Okay, so basically you have a piece of wire. Yeah, you have a piece of wire. You have a non-uniform magnetic field. Okay, and you're supposed to find the total force exerted on the entire section of the wire. How are we going to do it? Okay, so if it was a uniform magnetic field, it would be quite easy. You just need to apply, right, IL cross B, right, just your regular force formula. Force equals IL cross B. But now you know it's non-uniform. Okay, so you need to add up the IL cross B due to all of the, at every single point you need to add up all the IL cross B's at all the little points, right? And that's basically integration. Okay, so first of all, to set up this problem, we are going to consider the force exerted on a very tiny segment of the wire, okay, located at the distance x. Okay, so the contribution to the total force. Yeah, here's some buzzing. Okay, any questions at this point? Any questions? Anything to clarify? Okay, so the contribution of the force, right, dFB is given by I dx cross B. Okay, right, this is simply the application of the IL cross B formula because L is your infinitesimal section dx. Okay, so B is given by this expression, right, which was provided to you as part of the problem. So you just need to substitute everything in and evaluate it. Okay, so dx is pointing in the I hat direction because you are integrating in the I direction. So at the end of the day, you have Ix dx 2.3k minus 2j. Okay, this x over here comes from inside this parenthesis. Okay, any questions about this? This is the force exerted on a very tiny segment of the wire indicated by this black line. Now that I know the force exerted on a very tiny segment of the wire, I need to add up all the tiny segments. Okay, because this tiny segment is just any random general segment, right? So I'm going to add up all the tiny segments, meaning I need to integrate from 0 to 2. Okay, meaning I need to integrate from x equals 0 to x equals 2. Okay, when you do that, it's actually a very simple integral expression, integral x dx. And by the way, this is where the physics ends, you know, and mathematics is all a math problem now. Okay, you x squared over 2, you evaluate it and you end up with this. Okay, the total force is given by this. Okay, any questions? Okay, yeah, and they also ask a question, can the wire ever experience a force along the x-axis? The answer is no, because like we mentioned just now, IL cross B, right, is your index finger cross your middle finger will always be a direction that's perpendicular to both fingers. Okay, whatever the result, it always be perpendicular. So in the same way, the resulting force will always be perpendicular to L, since it's L cross B. Right, it will always be perpendicular to L, and it will always be perpendicular to B. Right, so your force can never be in the direction of L. Okay, any questions? Okay, otherwise it's on to, I believe, our last question. Is it this? Conductor in the square shape? Okay, so a conductor in a square carries a steady current of 10 amperes flowing in the clockwise direction. Calculate the magnitude and direction of the magnetic vehicle at the center of square. This is a super easy question. If you are familiar with the formula that we introduced in our formula sheet just now, okay, which is this formula. So if you recall, in our formula sheet just now, we mentioned that for such a configuration, right, the magnetic field at point P is given by this formula. Okay, so this is the formula in the formula sheet and which was derived in the lecture. Okay, so if we take this for granted, which we can since we derived it, okay, and we realize that a square is just made up of 4 segments of straight wire. Okay, it's actually very easy for us to just add it up. Let theta 1 be pi over 4, right? It's 45 degrees. Theta 2 is 3 pi over 3. Okay, there's a lot of buzzing again. May I ask if there are any questions? Okay, if there are any questions, please. Right, please feel free to sound out. Okay, if not, then let's, right, it's just a few minutes away from right the end of class, so let's, okay, try to focus, okay, it's just a bit of this question there. Okay, so like I said, right, in the lecture notes, are given a magnetic field for one segment of the rod, right, and a square, this question is made up of 4 segments. Okay, so adding up these 4 segments together, okay, simply involves adding up the formula for 4 segments, right, which is equivalent to multiplying it by 4, because you're considering the point in the middle of the square, right? And by symmetry, the contribution of each wire to that point in the square is the same. So just multiply it by 4. Okay, and you can check that the B field points on the page using your right hand rule, right? Once again, it's the right hand rule, right? But it's the thumb version now. You point your thumb in the direction of the current, and you can see the B field going into the page, right? You can do it for AB also, right? You point your thumb is flowing from A to B, pointing from A to B. You see that your fingers are going into the page. You can do that for every segment of this wire, this square. You see that your fingers are pointing into the page. Okay, so the B field points into the page. Okay. Okay, so yeah, indeed, you want to add them up, which basically involves multiplying by 4. So that's the answer to 8.28 microteslas. Okay, any questions on this, our final question? Okay, I was hoping we have a bit of time left over so I can talk about the questions from last week's tutorial. Unfortunately, apparently not. Okay, but please feel free to drop me email or Teams if you have any questions about it. Or if you want to come up here after, after we end the class, I'll hang out for a few minutes. You want to come up here and talk, I'll still be around, okay? Okay, I know everyone is tired after a long day, thank you very much for showing up for class, right? Hope you guys have a great rest of the week.
Thank you.
Thank you.
I actually